Yes, good evening. We'll wait for some time, then we'll start the session, like some 2-3 minutes. Okay. Fine. Or shall we start? Just that good evening, everyone. My name is MDS Brother, and I am PMRF scholar in the Department of Mechanical Engineering at United Trichy. and we are continuing that is the live session every week for the course of that is machine learning for engineering and science application. And we have came across like we have seen that many methods like deep learning and CNN and other methods we have seen. Then we came to the traditional method also. It's supervised machine learning, and then we have seen the ensemble learning. That method also we have seen around, like the bagging and boosting also we have seen. So now we'll continue with that also. I'll give just brief like before starting the session of that, and then we'll move forward. So I think till now we have discussed supervised machine learning. In that also we have the last class the bagging boosting was there. Then that decision tree was there. Then random forest was there. Okay. So I'll give just brief of that, and I'll take some like short time for a while. Then we'll go ahead with that. So now we are in the 10th week. Can anyone tell like anyone have the doubt any the question in the assignments and all? I think that you are solving that assignment problems also parallelly. If you are going to write the like you are going to write the exam to get the certificates and all. So I think that we have started with that introduction that what is the machine learning, where it's going to use it out, and then how it help in the current scenario also, even with the high tech or even with the defense applications also we can see around the people are using the AI and all. And we have two big giant like that OpenAI and then that Anthropic is there. That's what their model is. Cloud AI is there. So that too actually dealing with the very giant in the field of AI. But people are still coming up with the Gemini and Facebook that they have the Meta, and even the Copilot is there for the micro that is like for the Microsoft and all. So as we can see, like it's a very vast and very growing in the field of that's the machine learning and then AI applications and all. So to deep dive into that also, because now that they're giving that agentic AI, the people are coming up with that like we just give the prompt and then that we will get the response and all. But how it work, how they'll go in deep search, how they will do deep seek and also. So that's we have to know about that how they're going to skim the data, which data is going to that going to useful for us or it's not going to useful for us. So how we can differentiate and all, it's very critical task and all. So it's going to be like backend. Some of the AI they will be giving their that open access will be there. Open access is something like open source platform they will going to provide and all. But if some will be not given, it will be like something called tool basis. Like that they will give one app, just use you give the prompt, you will get the response. There's no much of detailing will be given and any other things will be given in that. So this is the one thing. So to learn about how the AI works, how the machine learning works, and also we should have some background in that. So it will start with the mathematics, and it's just 1 minute. Someone want to wrote something. Okay, so you have the concern about the exam pattern, question format, and access to the previous question and access to the previous question. Whatever I'm solving, that is the previous year question paper only, and then I kept in the previous assignment that I kept in that drive folder. Exam pattern, whatever what we are doing in that the assignment that you are getting, same pattern will be there, and the format will be same. Otherwise, any specific, so they will going to they will keep in that is that in announcement. So if previous year question paper will not have the that is the final semester exam, but it will be the assignment question is there. So that you can get the access through that one. I'll just show that where I have kept it. Okay, this is the 26 one. Okay, fine. We'll go with that. So actually, if, whatever the session I'm taking, that is available on the YouTube also. And along with that, whatever the content I'm teaching, that's also kept in the Drive folder. So that Drive folder is this one, like Drive, Google Drive I kept. So you can have the access when you go to the that website. So you can see around that every week the PPTs are also there, and even like assignment previous year assignment problems are also there. So like some questions will be there. That's how you have to solve it, and then you have to keep it in that the same pattern will be also in given in the what we can say exams also. Regarding that calculations and all, that might be giving that like online calculator will be there. I'm not sure about the exact pattern, well, whether it will be going to be uh, that's going to be heavily that it's going to be numerical and all. But I don't think so. The same pattern what we are getting in the assignments also. So let's say this is the assignment problems and all. For current week, I can't solve. Like for previous week, that's what I'm trying to solve here. First, I'm giving the brief and all. So this is the way it will come. What is the mathematical that is going to be notation for the Gaussian distribution, also known as going to be normal distributions and all. So that you will be knowing that. Just click the option and submit it. That's the thing will be there. So this is the same pattern what we are getting in the assignments. The same thing will be there. Previous year question paper for the final exam, that is like that not shared actually. So it will be same pattern as like what the assignment that have. So that you can follow through and go through the lectures and then solve it. It will be the similar pattern will be there. Anything other than this, if you have doubt, please ask. Is it clear or do I need to make some more clarity on that pattern? Okay, thank you. So we'll go with that, and even you can get the access of this drive link also. And I kept till 5 week I kept, and PPT kept till uh, 7 week. So remaining week PPT and then content I'll be keeping in the drive folder and all, that you can get the access through, and then you can go through that. Coming back to the our discussion actually. So actually we are verge of the completing of what you can say that our course actually, because we are already jumping into that like traditional method, that is the covariance matrix and then PCA and that SVM that we'll see today itself. In 11th week, what we have that multi-layer perceptron will be there, or generative adversarial that network will be there. That is the advanced machine learning technique will be, that will go very brief. In that also we have to take some examples, and then we'll solve some example. Then 12th week again we'll take some example related to the heat transfers, or maybe that blood vein problems, and then we'll solve it. So till today, like till this week, or maybe the next week also, we'll see that auto encoder. It's actually the part of semi-supervised that learning, or self-supervised learning, that what we have. And today, what we'll see, will be starting with like last week that we have end at the boosting. Then we'll jump into that unsupervised learning, like it's called K-means clustering, and then clustering will be there, and then K-means will be there. Then we'll go with the what are the distributions in the probability. Based upon that, what we have it, that the naive base is there. Then MLE actually is the maximum that likelihood functions is there actually. So how it will calculate and all that we'll see also. and then we'll go with the naive Bayes classifier. It's like it's based upon the Bayes theorem. Then PCA, just to based upon the variances, we have to segregate or try to try to reduce the dimensionality of that like data set. If it is 3D and 4D, and also we'll come to the 2D and all to better separation in the line and all. Similar way, support vector machines also there just to create a hyperplane, and then we'll get the results. And then in that also we have to calculate that linear SVM, or even with the what I can say non-linear SVM. In that we have to introduce the one factor. It's called weight function or objective functions. It's called sigmoid and all, and that the kernel based that the SVM will be there. So that will see today itself. So with this whole thing will completed. So where we were there. Before that, we have discussed the probability, how it going to useful out and all. I'll just switch off the camera here. Okay. So then we have went into the optimization. Optimization actually, why do we need? It's actually whenever we are going to solve the problems. So either thing we have to maximize or minimize. So anyway that the error is there, so we have to minimize the error. Minimize the error. So it's actually a optimization problems will be there. Optimization, it can be that's called maximization, or maybe that the minimization. And the thing is that in that we are when we convert to that matrices, it's called Hessian matrix and all. It will comes into the picture once you go to the machine. If you go to the first week or second or third week of the lecture, that you can see around. Then what we were having, it's called machine learning packages. Like the MATLAB have a statistic, and then machine learning toolbox is there. Even the Python have their own toolbox is there. And even with that C++ and all that, you can write the coding. Even you can write the by your own code, and then you can run it or not. Then we have started with the very basic regression method. In that, what we are having that the linear regression, and then we are having the logistic regression. Linear regression, that simply what we have, it's y is equal to mx plus c. Logistic regression, when we have nonlinear functionality, and even the logistic function will be there. So it's actually 1 by e to power n x will be there. So that's how we can solve it or not. Then how that underfitting and then overfitting can happen, it's called bias and variance. If it is bias is more, so it will going to replicate to the underfitting. Whatever the keyword is speaking, sometimes this can be also the question, because the similar question with that we have solved in the assignment problems also. So when the variance will be the more, it will call that so that the overfitting actually it's like this only. So here the bias will be more, and here the variance will be the more. This region will tell the underfitting, and this region will tell the overfitting. So this is the region actually, and this is the optimal region. Optimal region, for that we'll get optimized parameter for any model. Optimize parameter and all. So then we have seen the variant of the gradient descent. Gradient descent is let's say we have the dy by dx. So to get that maximum of that, so we have to take second derivative and all. MLE is something maximum likelihood functions is there, and MAP is again same terms with that. Then we started with that neural that the network, and in that also multi-layer perceptron, and then back propagation error. So we were having the forward method and then backward method also. So we have some differences between that. If we don't have much of that, what we can say, that a parameter or the variable, so we can go with the forward propagations and all. Once it comes to that, too many variables are there, so that's very difficult to calculate for each step, with using the central limit theorems and all. So we have to use the back propagation that use actually what I can say chain rule of derivative. Chain rule of derivative actually. So then after we went through that, when we have only one hidden layer, or maybe that perceptrons and also that will say ANN, like, and when we are going to have much more like a hidden layer 1, hidden layer 2, hidden layer 3 and 4, so it will come under the category of the deep learning. So in the deep learning, what we have is the CNN is there. CNN is actually like for that input will be the image classification that is done. So in that also that we have seen CNN operations, also CNN architectures, also that's how it operates. We have like block one in that first we have to give the image. Image will do the bit of processing, like it's, let's say, 64 by 64 or 32 by 32 of that either single channel or the multiple channel will be there. Then we'll give it to the block one. It will come to, they're going to try to reduce the dimensions of that. Then again, one more like that will be there. And then again, that second block will be there. The third block will be there. And then the flattened layer. After the flattened layer, it will go again to the closing up to the, then it will go to classify. So then, saying an architecture, actually it's worked like this is the image block 1, then one acquisition functions, again block 2, then flatten layer, then again block 1, 2, then again, then this is a classification model. It will be there. So what they will do, let's say this is a 64 by 64 is there. So they will try to first to reduce the dimension, right? Dimension reducing, dimension reducing, then we'll do the flattening. Then again we going to close up with that and we'll get the same dimension, but we get the classifications and all in the the last stage of the block and all. So then in the like further of that or advancement of the CNN, actually it's called transfer learning. Transfer learning is something that we are going to transfer learning is something that I'll tell you one thing. Like let's say I have some complicated catered model is there to classify. I have to get something. The thing is that when we go with the CNN, that might not get the good results. Or the thing is that before we'll do the preliminary classification by using maybe some traditional method like ANN, or maybe use the SVM. So now whatever the information will get from the like a preliminary trainings and all that we're going to feed into the actual CNN model or any other LSTM or GRU, or maybe that RNN model will be that will feed it. Then the same process will be there. So that's what they call transfer learning. Let's say we have one more example is there. Let's say I have one trained and one untrained group. So we'll take all the properties of the untrained one and then we'll feed into the trained one so that they can able to classify whether what's the difference between the that and all. So that's what we call transfer learning. Then this model is actually used for the classification. Either yes, yeah, either no, either the fatigue happen or not. So to overcome the thing is that whenever we're going to do that real-time applications or real-time something, let's say I have to do the forecasting of the trade market or share markets and all, or maybe forecasting of let's say that's the land purchasing to power and all. Just 1 minute. Okay. So for that, whenever the time and it is going to vary in the space, so then we have to come across the RNN. RNN is going to temporal spatial pattern recognitions and all. And to overcome of all this, also LSTM is the long short term that memory is there. So they can do with the regression. It's actually for the classification, and this can be used for the regression. Regression is something that we can do with the time, how it will be going to vary with that time and what is the price and all. So this is the things that so that we came across. So this is the whole thing about with the deep learning, and then that neural that network was there. Then in the last week, what we have done, we have entered into the classical techniques like regression used, we have used the binary trees. Binary trees, like it's based upon that entropy and then gene index and all that we have seen around. Then the similar way we have checked for the random forest, whenever we have the multiple trees are there that club with the uh, uh, like like trees and all. So it will go into random forest, make it and all. Then we have to start with the what we can say unsupervised machine learning and all. In that also we have seen the bagging and boosting. Bagging is something like we are going to take two bunch of the trees and then we'll came across and then we are going to make that the maximum of the whatever the, it came that the majority vote and all. Bagging is also a similar concept, but with the advance, with the error which comes into the pictures, or maybe that any feature which comes into the pictures and all. So that's how it worked out and all. So now we'll go with the unsupervised where it is last class. We'll go with the clustering actually. We have seen this around like how it worked, bagging gene index and all, and here the so that the bootstrapping will happen aggregation and then bagging will be and that will be the based upon the majority of that what we have. Then aggregating the results. Then we have that random forest is there. Random forest is something that if we see around, so we have that multiple tree will be there. One, two, three decision trees are there, and then from there bagging that is the like it's the voting majority, and then they're going to predict the class and all. So what is the things? So they will give the high accuracy because when once you take for the each tree alone and alone, so they might be not giving the better pictures and all. So that's what we can do with the like club at one place, and then we can do the voting that the majority and all. Then what is the difference between the bagging and then boosting is there. So bagging is something that I told original data is there. We are going to classify one, two, three. Then we'll do the aggregating, and aggregating based upon that like we'll do the majority voting and all. Boosting is something we are going to original data is the classifier, and again if not classified properly, so we are going to add the weighted data. Again we'll feed to the classifier. Again we'll go again keep the weight and all. Just 1 minute. So this is how it worked in the boosting till till here we have seen. Now we'll go with the unsupervised machine learning. What is the if we talk about the machine learning model, so we have supervised one. It will come in the NN, SVM, decision tree, random forest, and all. Then we have the unsupervised machine learning. In that, what we have is the K means clustering and other, and then we have the semi-supervised machine learning. Then we have ensemble learning. In that only what we have the bagging and then boosting is there. Then what we have the reinforcement learning. It's like based upon the penalty and a reward. Then one more is this. It's called self-supervised learning. Self-supervised. It's based upon the auto encoder. So this is the brief type of the machine learning and all are there. So now we'll see what is the unsupervised machine learning and all. It's unlabeled data, so we don't have the answer for that. So what we'll do, it's like fit into the structure. From the structure, like new unlabeled data, then model, then map the new data to a structure. It's something like we don't have that specific data set law. So what we'll do, we are going to based upon that their weight or maybe the class and all we're going to will keep in one group and then like we'll go into fit to the model, then we can fit to the structure and how. So how it will work out and all. Clustering is actually algorithm that group data point into the cluster based on their similarity or differences. Let's say what they I have one population is there. I got some data like 78, 69, 24. Just one minute. Okay. So we got the random of data. So what will be say? What are the like the for the population? What can be the things? It can be a gender, age, or maybe the weight, height. So these are things that can be classified in the. So what we'll say, we'll take like let's say that group, the age group will be there. So we don't know which one is the age, which one is the height, which is and all. So we'll take like we are going to based upon the similarity, or maybe it's the variances. If the variances is going to more than 5%, we'll not consider that now. The similar way we have to take the cluster or we'll take a group, and that can become a as a label data. Then we'll feed it to the model and all. So means like we have to make the cluster based upon their similarity or differences. If the differences is more, so it can be of either class. Either class means either group, not the class. I can say it's the either group. Similarity like it's let's say for that particular let's say age, I have taken the going to be a young age, so 18 to 30. So 18 to 30, if it comes that we can keep as a it's arbitrary or it's our assumption that we'll keep in that. So that's how the clustering will done. So K-means clustering group similar data point into a cluster without needing the data label. Like we don't know the data labels, but it still will take we're going to make the cluster based upon the I told similarity or maybe that variability and it used to uncover hidden pattern when the global goal is to recognize the like data based upon the similarity. So what they will do, so they will going to help identify natural grouping in the unlabeled data set. I told like age. So if I have specified the young age, so it can be 20 to 25 only. So whatever the value it came from the 20 to 25 will keep in that group, in that cluster. But the thing is that I am going to create. Sometime what happened, let's say 78, 48, 60 and all. And the thing is that some might have weight of the 24 also. It could have been truly in this weight. But the thing is that it might have weight into that. So that's why we have to so it can be, but the thing is that we have to take the some 5% or some 3% or 7%. It's based upon the what we need. So works by grouping point based on the distance to cluster center. So it's again we have to be calculate the Euclidean distance and all. Commonly used in the customer segmentation, image compression, or pattern discovery and all. So whenever we need the structure from the raw and unorganized data and all. So how they will do it? They're going to, we are given data set of the item with certain feature and the value of the first feature is like a vector. So the task is to categorize those items into the group. So this achieve will use the K means. K means K represent the number of the group. K means number of the group. Let's say I set the like a population. When I set the population, it means like something like we have age, gender, weight, and all these are the some number of groups can be there in that population. So that will say K. So choose the initial centroid. You have to choose one, two, three. Then after assign point to the nearest centroid. Like it's something like cluster centroid is that. Then we have the cluster one, cluster two, cluster three based upon the centroid distance. Then update the centroid. Like let's say once we calculate, so again from there we have to calculate the new centroid from the corresponding this one until the unless like that we can't move forward. So here the data segregation was more. Here it becomes some closer. Now we can see one group, this yellow one group, then the green one group that we have. So that's how they are going to cluster the data. It's like how we are going to update in each every step to centroid distance between the one point to the centroid and all. Okay. So how they're going to that the algorithm will categorize the item into the k groups or cluster of the similarity. To calculate the similarity, we'll use the Euclidean distance. That the same what we have used in the in which the so that the last class we have seen. What was that? Dysentery. Canaan. Canaan. Dysentery that we are going to use entropy and then Gini index for the classifications and all. But the thing is that for the Canaan we are using the Euclidean distance. Like it's a k nearest neighbor. So what they will do, they first are going to initialize. Will begin randomly by selecting the cluster centroid. We don't have. We'll going to initiate one, two, three. Then we'll calculate from each and every data point, and then we're going to give the each data point assigned to the nearest the centroid from the cluster. Update after the assignment. We recalculate centroid of each cluster by averaging the point within it. Then after it, we're going to repeat until there is no longer change in the in the centroid and all. So here is actually what they will do. The goal is to partition the data set into the k cluster, such a data point with each and cluster more similar to the each other than to the those or the in the other cluster. It's something like we have to just classify. It's making the cluster. Let's say I have a group of the people are there. Let's say I have in a college that so that is the one fest is happening. All people came, B Tech, M Tech, female, male, even the faculty staff and all. So now the thing is that now we have to categorize it to make the cluster. So now we can make the cluster based upon their properties. Like that's called algebra distance. So we're going to make one first cluster based upon the B Tech people, M Tech people, PhD people, staff, and then faculty. So that's the five cluster came into the picture. So that's what they will going to do it on all. So why we're going to use it out for the data segmentation. I told like when in a fest, it can be the multiple peoples are there, staffs are there, faculties are there, students are there. In the students also BTechs are there, MTechs are there, PhD are there, other like peoples are there. So that we can do the by clustering, we can use the segmentations and all. So even with the we can use for the image comparisons also. So that will going to reduce the complexity of the image by grouping similar pixel into the cluster. Let's say if you see in the picture, when we talk about the picture, we have to talk about the based on the pixel. We are not talking about directly with the image and all. So we have to talk into the either if we have the black and gray, so it will not going to speak like in, but RGB is there for the color. It's the red, green, and then blue. So based upon their intensity, what we have. So if we have multiple that image are complex, so what we'll do, we are going to make the grouping into the similar pixel into the one cluster. Then effectively we can compress the image and all. So actually, this is going to be useful for the image storage or maybe the processing also. Then that the anomaly detection, like it's applied to anomalies or outlier by identifying the data point that not belong to the any cluster. It's something like let's say sometime in the any data will be the outlier. Let's say in the group of the people, I want to cluster with the only BTech people, but somehow it came the MTech also, so that we can do the elimination of that MTech to the from the our group or the cluster, or even with the document clustering also we can do, and organizing the large data sets also we can check it out. So now we'll come to the k means like algorithm. So it means like with the algorithm minimize the cluster variances. Like it's something here we have to minimize the variances in the cluster. Then after we have to update it, and then we can get it. So data sample is the K cluster, split data into the K cluster where each cluster is given by CK, and then contain the I index of the data sample that is assigned to the cluster K. So it's something like it's a repetitive data process, and then we have to calculate and all. So it means that the variance should be less. So now we'll come to the like it's called hierarchical clustering. Hierarchical clustering is something like unsupervised learning technique that group data into the hierarchy of the cluster based on the similarity. If it is higher similarity, we'll keep at the top. Then similarly, it's like a tree-like structure, like a dendrogram. That will help to visualize the relationship and decide the optimal number of the clusters and all. So it not required the pre-selecting the number of cluster. We don't have to set like three. For the clustering, if you see that we have to decide the three cluster, four cluster, five cluster that we have to decide. But here we can't be based on that. So here we are going to use the agglomerative and divisive approach. It's something like a divisive and like approach we have to use it out. Just 1 minute. Okay, so in the hierarchical clustering that we are going to use the data into tree instead of nested cluster. We're not going to give a two or three clustering that predefined and then we're going to it going to nested into that. So here we'll do the based upon the group of the data. It's based upon the hierarchy of that based on the similarity or maybe the variances also we can say. So that's what they will do. It's a level one, then whole group will be the level two, then the level three will be there. So it's again here that like dendrogram will be there. A, B. From there also we can come the C, D, and all that we can come across with that. So if you see like how they will going to do types of the clustering, it's based upon the agglomerative and then divisive approach and all. So ABC is there. It's again A from A the BC, then again BC. Here DEFG we can divide into a two factor like two groups, and then again it's like a division base. That's the level one. It's alone singular, then the level two, then the level three. So here what they will do, minimum distance either based upon the maximum distance or maybe the group average or maybe the Watts method. Watts method is like something like we have to get like 1, 2, 3, 4, 5 like that, but and all we can do. So where we can use it out, it we can use in the portfolio construction and optimization techniques. And let's say portfolio where we can use it out like I have a share market is there. Now the thing is that I'm going to apply for the small stock or maybe that large stock or maybe the penny stock also. So now, based upon the when the reward will be high, so their penalty will be also like high will be there. So now we have to define. Okay, we have the very high risk, so where there so there will be reward will be also more. So that's how we can do it allow. Then we have the sector and industry analysis also. Pair trading strategies also. Like we can take two groups from here or either from here to here or either from here to here. So again, the behavioral financial analysis also we can check it out, and it's something like we have to make the some sort of pattern and all. So now we can see. Imagine what we have. We have the four fruits are there with different speed: apple, banana, cherry, and grapes are there. So the thing is, that start with the like each fruit as its own cluster. Okay, then merge the closest into the 30 and 50 are the first group. Then after Apple and all next one group. Then finally these two clusters merge into the one. That's how the like dendrogram is going to make it out. One and it's one. So now it's become these two clusters it's again going to merge it into the one. First we're going to make one this, then after it become one. From here also, from there it came, it's similar to like this. Again from here, whatever its output came, again we can join it here. Again we can join it here. Like it's similar way it can go. Or either way also we can go. We have a two. From here one came, one. From here also one output came. Then again we can divide into two. The similar way we can go. So dendrogram is a like a family tree for the cluster. It shows how individual data points or group of data merge into the together based on the similarities and all. So I'll not show the models and all, like I'll just explain how it works and all. So even when we'll solve some examples and all, I'll show some so that the last class I have shown some codes also how it worked. So for all this, what we have already machine learning toolbox and all are there. I can show you in the MATLAB also. So if we go to the apps and we can go to this one and we can see machine learning and deep learnings are there. So we can see classification that the learners are there. Then the neural need to fit with them. Then we can go here. Once you open that one, so in that only we can see the thing is that how we can segregate the data, how we can give the data and all that we have to see around. It will open. Here with, we have the PCA is there, test is there. We can only check the all the that the model. Let's say I will be going to take some data. Let's say I'll take some random data. Let's go somewhere here. I don't have much of data. I'll just check it out and I'll tell you. We'll come back here. Okay, so we were seeing around we have the two types of the hierarchical clustering was there. One was the hierarchical agglomerative clustering. It's called bottom up approach. Bottom up approach. From the bottom, it's known we'll go bottom up algorithm. Treat each data as a singleton cluster at the house, then successfully agglomerative pair cluster until all clusters have been merged into the single cluster into the. So it's alone single and all it can go. From here it came directly BC one group they created, CD one group they created. Again now BC actually is there, or maybe we can go from the here this side also. It's ABCD and there. So how we can calculate then from the BCDEF. Then from here we took the DEF, again DE, and then F came here. So that's how it will go until all clusters have been merged into a single cluster and all. So earlier it was the all cluster was there, six cluster was there. Now it's alone based on the similarity and all we can go. So start with the individual points. Each data points has its own cluster, and the five data point start with the five cluster. Each contains just one data points and all. Calculate the distance between the two clusters, merge the closest cluster, and then update the distance matrices. Then we have to create the dendrogram. Okay. So now we'll move forward and then we'll go to the next, how we can see the data. And if I'll show here, so we will see something like MLE and then some of that probability distributions and all. So if we talk about the data set of how many data set what we have, it's called data set will be that descriptive data set. Anything is there? Anyone is asking? Now I'm going bit of a statistic also. Little bit like that, not going too much. So what we have is the frequency distributions, let's say 5, 10, and 10, 15, and then that's we can make the histogram, or maybe the graphical representation also, graph or table, or a summary statistic like describe based upon the what you can say data number in that mean, that median, and all. So if you see around, so the order array is a listing of the value of a collection in order to match it from the smallest value to the largest value. It's something largest, second largest, lowest value. So frequency distribution is a structure where make it easier to grasp the distributions of the value. Let's say this one, 40 group, 50 group, 60 group, and all. So we can make the frequency in that also 1, 2, 3, 4, 5, 6, 8, 9. So that many numbers came into the picture. So actually they're going to reveal the pattern and trends within the data. Okay. So they're going to reveal the pattern and trends in the within the data itself. It will not give the clear picture, what is the mean, what is the mode, what is the standard deviations and all that, not give the clear pictures of that. So we are going to histogram is something we may display like a display of frequency distribution graphically in the form of the histogram. So how they'll do it? Let's say I have the true class limit. For this limit, how many numbers are there? 11. For this limit, what we have, that much number is there. For this much limit, that we have this much numbers are there. So we can make it out. So a histogram, the value of the variable under the consideration are represented by the horizontal axis of frequency distribution now. So how it will show? It will show like this. So for that particular class limit, this much number or frequency what we have, for this much what we have this much channel. So this is, it's just show the trends or the patterns and all. Even if we go to the solve the machine problems and all, so we have to show around what is the pattern, what is the mean, what is the mode, what is the dispersion, or maybe what is the quarter and all that we have to show around. So this is the how frequency polygon, until unless like we have drawn the histogram on that point, just draw the straight line. It's called polygon. Histogram polygon. No. A frequency distribution can be portrayed graphically in yet another way of means called for which is a special kind of the line graph. It's something line graph connecting class middle point. Earlier we have the all the frequency. This is the histogram. Now take the middle point of this class and then it become frequency polygon. Let's say I'm going to say in the machine learning, like I have taken some data and all. Before the data, like we have to check whether how it, what is the trend pattern, how it vary, and how we can classify, whether the data is significant or not. So that we have to check it out and all. Then again, we have what we have is the OGIV. It's called cumulative frequency graph. It's to start with the that's the lower class, upper class, and upper class, and upper class. So help to visualize how frequency accumulate over the class interval for your data will plot the less than O give. Cumulative frequency versus the upper class and all. So that's how it start with the lowest, it will go away. It will not start with the each class that the middle point and then like this, then come back. It will go with the lowest, then further it will move to the upper class and so on. It's called O give. Then that we have the pie chart. Pie chart is again to show with the how the distributions are happening to visualize the proportional distribution of the frequency across the class intervals and all. Okay, for this much, that much number is there. For this group, this much numbers are there. So that n1, n2, n3, n4, n5, and all will be there. So then what we have, the data can be static also, dynamic also. Static data is something like we'll get test score of a batch. First batch, this much score. Second batch, this much score. When dynamic data with the time, it will change. It will change. That's how it came around. So data that evolves over the time, collected as a time dependent sequences, and then used in the monitoring and predictions. Okay. So that is going to help for the heart rate over the time, like when the time going, how it going with the like vary with the when I am doing the this is going to heart rate. This is the workout time. Less time, let's say 10 minutes. That the normal heartbeat was the beat per minute. When increased, it went up to the shoot up to the maximum, and it can go up to the that. So that's the limit only. Only. Okay. Then what we have the time series bar graph is it's again a dynamic data. Dynamic data will be there. It's going to represent the data point in the chronological order. Let's say it's a time inches measured value. When the time went up, it went somewhere value. This came down. It's something. So actually, it's going to be useful for the analyzing the trends, seasonality, like changes over the times, and even with the combined with the biomedical finance or ever even with the weather forecasting also. Then one more what we have that you might have heard too many times, like it's a box plot. Box plot is something. It's a graphical summary of the data using the five number summary. That's called minimum. It's a minimum. Then the smallest non-outlier value. It's like we have this box plot. Beyond of that point, it can be outlier, but this one is not outlier. Okay. Q1 is the first quartile. From here to here, lower quartile, upper quartile, then the median. Median is the 50th percentile. It's a middle value. Then the Q3, 75 quartile. Then maximum is the large. So interquartile range will be the Q3 minus Q1. So this is called IQR. So IQR represent the range of the middle 50% of the data, help measure the variability robustly. It's less affected by the outliers and also. So how can we get the outlier rule? Q1 minus 1.5 into the IQR, Q3 plus 1.5 into the IPR. IQR, not IPR, IQR. So let's say we have the data set 5, 7, 8, 9, 10 and all. So figure, box plus, data manual box plot title and all. So we can see around that how we can box plot the data. We have the one that command is there. Box plot of that data itself. So they'll calculate the Q1, Q2, Q3, then minimum, max, and all. So this is the one outlier is there we have. So it's all the range of the 18 and then 50 is the one outlier. Then what we have the spider plot. Spider plot is something display the multivariate data. Like let's say rest, moderate, and fatigue. It's a we have the 3, 4, 5. It's called radial diagram. Okay. Each axis represents the different variables used for the comparative analysis across the category. Okay, that's going to use in the biomechanics, sports science, medical diagnostic, and all. In the biomedical applications, it's mostly used and all. Okay. So now the thing is that now we have the data, we have visualized it. Now how can we like going to summarize it? So there are we have the two way measure of the central tendency. It's called typically average score. Then what we have is the measure of the variability. It's called a typical average variation. Just 1 minute. I'll come. Okay, so we'll see around. What are the types? Like, how can we summarize the data and all? So one is that what we have the measure of the central tendency. It's going to measure the what central tendency. Like let's say I have the data 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So where the it going to lie the central? It's understand the center or typical value in the data set and all. It's the first one is that what we have the mean. Mean is actually a arithmetic average for the country data. Median is the middle value, then the mode is the most frequent categorical data set or discrete one. So mean actually we'll get whatever the number of data sets is there, we'll go to summation it and then divide by the numbers. So due to data will be symmetric, no outlier. So that the median can be some sort of skewed data, outlier can be there. The mode, most frequent value, categorical, or it can be a discrete data will be there. So how can we do it? Like it's something a measure of the center tendency is going to give us the center, but we also not know how spread the data is there. Okay. So the thing is that we know the thing like where is the mode, where is the mean, and then that the median is going to happen. But the thing is that how the data is going to spread out. What is the variance? What is the range? What is the standard deviations? What is that degree of coefficient or the, like degree of freedoms and all? Okay. So measure of the like dispersion is actually a like variability or a spread of the data around a central value. It's like something like how it going to vary like this, or how it vary, or what is the range, what is the range of maximum or maximum, like that's all we have to see around. Important for the understanding the consistency, identifying the outlier, or interpreting the risk. So what we have the range, variance, standard deviation, degree of freedom, coefficient of variation. We have seen the quartile already. IQR we have seen. Then we have the cortices and the so range will be the always max minus mean. Like what will be there? Maximum minus minimum. But sensitive to the outlier. If it is the 1, 2, 8, 10, 15, 18. But the thing is that one outlier is a 60. So what will happen? It's going to make some drastic change in the range, you know. Then what we have the variance. It's a average squared deviations. Let's say we have the actual central minus central one and then actual value. So then we have to do the square of the error. It's actually an error. How much variation is there? So y to square to avoid the negative, emphasize the large deviation. Then what we have the degree of freedom. When estimating population variation from a sample, different will be the number of 1 minus 1 because the one parameter we have already calculated. What is the mean already calculated? So it's going to be degree of freedom will be n minus 1 always. Standard deviation is square root of the variance. Then coefficient of variability it's going to standard deviation by mean. So relative the measure of the variability actually. So it's going to be a unitless compare across the different scale. Mean standard deviation 10. Mean 10, standard deviation 10, CV will be 100% and all. Then what we have the percentile and quartile. Percentile value below which X% of data will fall. 90, like it's like 90th percentile. It's going to value below which 90% of the data will going to lie. Quartile means we are going to divide into the four equal parts. Q1 will be the 25th quartile percentile. Q2 will be the like a 15th. It's called a median. Then we have the Q3, 75 percentile. Then what we have the interquartile that the range is there. It's called 50%, middle 50% of the data. Like let's say this is going to be a min, max, idle, min, max, ill. Like it can go. Then Q1, Q3. So interquartile range is this one. Okay. Then it's going to robust to the outlier. Cadence is going to measure the tailedness, like how it's going to like vary. Like they are tail flat, and then it's going to put a full flat. So then we'll come across the probability also that we've seen is starting itself, but we'll go with the naive Bayes theorem also. Like a probability, that what we have, the one is the event, one is sample space. Event will be something that is going to happen. Let's say I'm going to coin the task, toss the coin. It's either it can get that the event can be either head or either tail. But the sample space will be the head and tail. Both will be the sample space. So that's how the things will go. Probability measures the likelihood of an event occurring. So the value range from the zero, it can be impossible. When we'll do something, so there is always chance will be there. Something will happen. Some event will occur. There is no chance that it is not going to happen. Let's say I'm going to toss the coin. So either head or tail. So there is chances of the 50-50. So there is no chance that it will not happen any event. Okay. So one is a certain. It can be I tell head, it happen head. It means certain. So we have the theoretical probability, empirical one, and some subjective one. So that we'll see based upon the logical reasoning, and empirical that we'll see based upon the experimental, and subjective probability is going to be based upon the belief or experience. That but we'll more of discuss about the empirical or theoretical only. So sample space, all possible outcome. Let's say for a coin toss, head or tail sample space, event is subset of the sample space. It either head or either tail. So what is the axiom of the probability? It will 0 to 1. Summation will be the always 1. For mutually exclusive event, P A union B will be always P A plus P B. Because mutually exclusive, so P A into P A, sorry, P A intersection B will be the always 0. The theory of the probability, like it's just 1 minute. We'll come back. So now we'll come to the, now we are going into the new base classifier. So that just by making the grounds. So in the all occasions of the set of all possible may constitute a subset of the total group. When the when the probability calculated with the subset of the total group at the denominator, result is the, so let's say I'm going to calculate conditional probability of A given B. I'm going to calculate the probability of A when the B already happened is equal to the probability of the A intersection B divided by the probability of the B that already happened already. So probability so it cannot be zero because already that thing happened. So that event already happened. So now I'm going to find out the probability of A when already the B already happened. So in that case, probability of A intersection B into PB. So this is for one. Similarly, we can go for the multiple events. It will be the so the in that case we can apply the chain rule. For let's say A, B is the last. So A C C B C D D E E F and then last E B. It can come. So it's a chain rule that the chain multiplication we can apply and we can get it out. So that's the similar way for the naive Bayes classifier also is there. So then what we have the joint probability 1, 2, A, B, A union B. That's how these things you could do. Two characteristic at the same time. Then what we have the multiplication rule is there. A probability may compute from the other probabilities also. For example, a joint probability may be computed from the other product of an appropriate marginal probability and appropriate conditional probability. This relationship is known as multiplication rule of the probability. Like it's something like we have the other group. One is the conditional one, second one is the marginal one. So addition rule, PA will be PA plus PB minus PAB. Whenever the independent event, so PA intersection B plus PA into PB will be there. Mutually exclusive, P in mutually exclusive will be that will be 0. Complement of the event, like what are the event happen there opposite. It can, let's say PA already happens. So what will be the remaining 1 minus PA? It's called complement. Then what we have the Random variable. Random variable is a variable that assume numerical value to the associated with the random outcome of an experiment. Let's say I have the coin, like toss the coin, head and apple. But if we assign some value, numerical value, let's say 0.5, so that will become the random variable. In the random variable also we have continuous like random variable, discrete random variables will be there. Okay. So types of the random variable, it's going to be a discrete one, number of sales, number of calls, people in line, and then mistakes per page. Continuous one, length, depth, volume, time and weight. Okay. So cumulative distributions, sometimes it will be the more convenient to the work with the cumulative probability, like probability distribution of the random variable. It's something like I'll not go much of like detail. I'm just giving the just brief like how the things will going to work it out in. So it's again a number of program so then the frequencies are there. So it's going to be like a discrete word, but here it is actually continuous one. So the mean or expected value of the discrete random variable will be mu summation of x px. X the particular number and corresponding the probability will be the will be having the mean value. The variance will be the x square px. So that's the that is the error. That is the error, the corresponding probability. So if we simplify it, we'll get x square px minus mu square today. Then one more the thing is that we have the binomial distributions. Like it's a binomial, like a sequence of the point trial form a process under the following condition. Each trial in one of the two possible outcome will be the mutually exclusive. One will be not going to fully depends upon the another one. Let's say I have tossed the coin. So first, let's say it happened either the head or tail. So second one, it not be affected with the one. So that's how the things will go. So probability of the success denoted by the P remains constant from the trial another. So the probability of the failure will be the 1 minus P is going to denoted by the Q. So trials are independent. Let's say I'm going to throw a dice. Throw a dice. It will come 5, 4, 3, 2. First one, it can come 1 to 6 anytime. But the second one will do, it not going to dependent on the previous trial. So all trials will be the independent of each other. So that's how the binomial trials actually, or binomial process is called. So now the what we have the binomial distributions. So binomial distributions. So NCX, P to the power X, Q to the power N minus X. If we take the number of successes as 0, NC 0, P to the power N, and the 1 will take black and then we'll do the summation, it will come always the 1. Always the 1 it will come. So what is the mean? It should be the NP. What is the variance? NPQ. Standard deviation will be the. So their derivations. So you can see any statistic book. Okay. So now what we have the Poisson's distributions. Here, when the probability is going to be higher, let's say I'm going to toss the coin. So what will happen? It's a 50-50 or an n is going to less. But in the case of so distribution, it's a number of occurrence will be the more. Let's say n will be the more, but the probability of occurrence will be the less. Less. Okay. So in that case, we have to use the lambda is equal to again np will be there. So it's called Poisson distribution now. So this is the one example that we solved for the like previous for the statistic for biomedical engineers. So a car for hire firm has a two car which is hires day by day. So that the number of demand for a car each day distribution as a Poisson so lambda is equal to 1.5. Calculate the proportion of on which neither car is used. Means x is equal to 0. Again apply e to power minus lambda power x factorial. So lambda is equal to 1.5. We can keep it out. And then second one, some demand is refused, means they have the two cars, but the demand was, so it's going to x greater than equal to 0. So in that case, 1 minus p of x less than or equal to 0, 1 minus p of x is equal to 0. When was there? P of x is equal to 1, then p of x is equal to 2, then we calculate. Then what we have, the continuous probability distribution. Like it's a, earlier we have seen the discrete one. Now we have the continuous one. It's again with the x and y, it's going to vary like this. Okay. So for that, what we have, the uniform distributions A, B, C, D, and all. So B minus A by D upon C. Like we have to take the either one, two value and all. So mean will be, mu will be C plus D by 2. The standard deviation will be D minus C. So again, the derivations you can go around and check it out. Okay. Then now we'll come across the normal distributions. It's actually normal distributions actually that we have the Gaussian distribution, that the covariance and all. So actually fx is equal to 1 minus root under 2 pi sigma. That we have seen one question actually. It's a like direct question we have seen. It's this week only. Yeah, we can see Gaussian distribution. That's also known as normal distribution. That we can see which is the formula like 2 pi sigma square x minus mu whole square by 2 sigma square. So this is the B. Can come the question answer. Okay. Ah. So characteristic of the normal distribution will be the, how it will go? It's going to be always a symmetric about the mean. Always mean. The mean, median, and modes are all are equal. The total and under is a curve, it will always the one. That we already know because the summation is always area in the curve will be the one itself. And the thing is, because of symmetry, already mentioned 50% of the area is going to right to the perpendiculars erected at the mean, 50 like a 50% to the left. This side with the 50%, 50%. Standard normal distribution that we have to keep like z is equal to x minus mu upon sigma. So we'll get the fz is equal to 1 by 2 pi e to the power minus z square by 2. So here mu is equal to 0, sigma is equal to 1 in that case. So how it's going to vary it out? So symmetric Bell density function and 60% of the area for the curve between the mu plus minus sigma, mu plus minus 2 sigma and all. So 95% and 97% all. It can't be become always 1. Okay. So that type table also you have to see on jet table. When the z is equal to 0.745, 50%, 1, 68%, 1.96. It's actually z will calculate x minus mu by sigma, not directly. Okay. So z is equal to 3. So based upon this only, it came 6 sigma, 4 sigma, 2 sigma, like that manufacturing. It means that the error will be the less. Like they're going to cover when we increase the z, what will happen? It's going to, or maybe that like sigma 1, 2, 3, 6 sigma and all. So what will happen? So that the coverage area under the curve is going to increase. So I mean, there is chances of the error will be the less. So that's how you will heard about any of the industry. Like let's say they're working on the 6 sigma, 2 sigma, 4 sigma and all. So means it's going to reduce the error and they're going to broader their inspection cycles and all. So the same way. So now we have the one more thing like what is the covariance matrix? Covariance matrix is actually that is the matrix to describe the covariance between the two random vector. It's a variance, covariance, and x1. It's a x1, 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 x2, x2, x1, x2, x2, x1. This is actually a variance. This is going to be a covariance. So like the variance covariance matrix is a square with the matrix with the diagonal elements that represent the variance and the non-diagonal components that express the covariance. Non-diagonal elements actually represent the covariance. The covariance of the variable can take any real value. It can be positive, it can be negative, it can be of zero. Okay, it can be of like positive, it can be negative, it can be of zero also. There is no much issue will come into picture. A positive covariance suggests that two variables have a positive relationship, whereas the negative covariance, it means they do not have the like like a positive relationship and all. Okay. So let me. If the two element does not vary together, they have a like a zero covariance and all. So how it will look like? Covariance matrices, variance of 1, covariance of xn, x1, xn, x1, variance of xn. So sample variance that we have taken out like x I minus x bar upon that. Sample covariance will be the 2 factor, not the 1, it's a 2 factor. Population variance will be the n minus 1. Why sample variance will be the, again because of 1 already sample that happens, so n minus 1. In the population, it's already 1 populations are there, it's going to n. So, property of the covariance matrix is something. It's actually a always a square implies that number of row in a covariance matrix is always equal to the number of column. It's going to always a square matrix. A covariance matrix is always symmetric matrix. It means transpose of the covariance matrix is always equal to the matrix. It's a symmetric matrix. A covariance matrix can be always positive or semi-definite. It can't be a negative value. Negative matrices, I'm saying, I'm not taking, it can take the value, either it can be negative, positive. It inside, it can be of negative, positive, or anything, zero also. But matrices, it will be the always positive. Like it's the value will come out, it's going to be always positive because its eigenvalue of the Covid matrix are always real and non-negative. Because its eigenvalue will be the always, I'm saying inside of the component, it can be taken as a negative value. There's no issue. It can take as a zero value, no issue. But once you calculate the I or eigenvalue, it will come as a like positive only. Like it will be the real or the non-negative only. Okay. So now we can see around we have the A, B, C. So physics, they got the marks 92. Biology, they got 80, 60, 30, 100, 70. So now the thing is that we have to calculate the covariance matrix. Again, maybe that you will feel a bit of boring that I'll show you the content for this week actually. So it's actually shown as a distributions, Gaussian, Bernoulli, then that's the covariance matrices. Then we'll go to the central limit theorem. Then we have the neo base, then PCA, that the principal component analysis, and then what we have, just 1 minute. PCA will be there, then the support vector machine will be there. So this is the whole agenda for the today class, and then we have entered into the covariance matrices also already. So covariance will be, I'll not calculate by myself. It will take much of time because we'll cover some more topic around that, and we'll wind up by 8:45 or 8:50. Okay. So we have to calculate the covariance matrices. The how we have to start from the like variance first, then the covariance. So mu x and variance of x, then mu y. Then we have to calculate the covariance of x and y. So we'll get it out now because it's a symmetric matrix, so we'll not change and all. So we'll calculate the one single covariance. We'll get it to directly answers to it. So now the thing is the central limit theorem. Central limit theorem is simply they will state if you take the random number or like random populations and all, if you average it, it's going to become average will become how normal distribution. Let's say this curve I took, this is the one curve, this is the one curve, in curve. If we average it, it will become the normal distribution. Or either if you increase the number of samples. So it's going to take the shape as a normal distribution and all. So means a bell-shaped curve, even if the original data is not normally distributed, as long as the sample size is large enough. So means when the sample size is going to be large enough, it's going to behave like a normal distribution. So this help us to make predictions about the whole population using this just simple sample data. No. So how it going to work it out and all? So central limit theorem, Z is equal to x bar minus mu upon sigma upon n. So it's the population mean. Standard deviations by n or sample standard deviation. So what are the assumptions? Its assumption is something the sample must be chosen randomly to fairly represent the whole population. It's like a random sample selection. Okay. So then what we have the independence. Each data point should be independent. One should not influence the one another. Let's say I have taken some sample, so it's not drastically reflect or influence the other points and all. And then one more thing, a large enough sample size, at least of 30. If you have gone through the t-test and all, so t-test actually used for the small sample size. If we go beyond of that, it's going to curve or it's going to what over the normal distribution and all. So means we need at least 30 sample for the to say is this is going to be a large enough sample size. Then what we have the finite mean and variance. Population should have the definite defined average and variation. Otherwise, what they will do, it's going to make the z is equal to unlimited. So this is how the things will look like. It's going to, if we take 1, 2, 3, 4, 5, 6, so it will eventually will make the normal distributions. Okay, with the mean 0, sigma is equal to 1, and all. So now we'll come to the new base theorem. This is actually a new base theorem. So Naive-Bayes theorem is a machine learning classification algorithm that predicts the category of the data point using the probability. Let's say I have to define the class, one class, second class. What they will do? How much percentage of the things is going to be like one class, second class. So it assume that all features are independent of each other. Means it's not going to reflect or it's not going to influence any other data points and all. So Naive-Bayes perform well in the many real world application like it's a spam filtering, document categorization, or sentiment analysis. Its original data is there. Estimation of the first dimension will calculate the p is equal to x, p of x1 at y is equal to 2, p of x1 at y is equal to 1. It's a conditional probability. Okay. Then we are going to categorize estimation of the second. Again, we'll take the p of x2 as is equal to y is equal to 1. Again, we'll take until and unless it's going to make parallel for the both. Okay. So it's perfectly classify the in any planes and all. So that's how things will work out on. Okay. So original data has a two class, green circle and the red circle. Estimate probability distribution along the first dimension. Estimate the probability like a probability distribution along with the second dimension. Then combine both using the conditional independence. Okay. So means P of x1, P of x1, y is equal to 2, P of x1, y is equal to 1, P of x2, y is equal to 1, P of x2, y is equal to 2. Then it will segregate the data like this. Second. So means first one what we have the y is equal to 1, y is equal to 2. Now we have to calculate the P of x1 for y is equal to 2 given. For P of x1, y is equal to 1 given. Then after second one, P of x2 for the y is equal to 1 given, P of x2 y is equal to 2 when the y given, then we have to combine with the conditional probability and all. So what are the features are there? That's going to be based upon the Bayes theorem to classify the data based upon the probability of the different class given the features of the data. It is used for the mostly high dimensional text classifications and all. So actually it's a simple probability classifier, but it's a very powerful actually. Sometimes this model itself can give the better results as compared to the some complex models and all. It has very few numbers parameters which are used to build ML model, then can predict at a faster speed than other classification algorithms. Okay, so sometime, so that this model can become very powerful or even very, just 1 minute. Okay, so where we were like it it is a probability classifier because it's assumed that one feature in the model is independent of the existence of another feature. It's something very important part. Whenever one feature is going to like have a dependent on another feature, it might this model will not work better way. Whenever the one feature is totally independent of the another feature, so this model will work very perfectly and all. So actually, it's going to use in the spam filtration. Either it's a spam or not a spam. Sentimental analysis, classifying the articles, and many more and all. So now we'll come to the like how the things will go. Getting the pet, like probability of the dog is the zero point 0.5. Probability of the cat is the zero point 0.5. So now we have the pet is very quiet. When the pet probability of the quiet when the cat is the 80%. When the probability of the quiet when the dog is the 30%. So means now apply the like base theorem. Like let's say I am going to say like now the things like when the cat is there, then when the quiet was there. So probability of the quiet cat is with 72%. Then when the that the quiet is there, for getting the dog, how much is that? 27% will be there. So that's how the things will going to work it out. It's adjust the probability when new information comes in and helps them make better, better decision in the uncertain situation. Like it's going to continuously, it's going to adjust the probability and all. So now the base term that we have seen around already, and similar way. Okay. So then what we have the hypothesis, like refer to the possible event or outcome in the sample space. It can even one, two, three. It's a hypothesis. Prior probability is the initial probability. Prior probability is the initial probability of an event occurring before any new data is taken into the account. It means is a existing probability. Okay. Then what was the posterior probability? So it's a dated one. Posterior one, it's a updated like a probability of an event after considering the new information. Then consider probability. It's represent the probability of the A when B already happened. Joint one is something the common between the two events A B. It's a joint of P of A union B. So Bayes theorem is something derived using the definitions of the conditional probability. It used to find the reverse probability. PB of A, PB of A, and then BB. Then concept of like a conditional one is the when one event, what is the probability of event A when already B has already occurred. Purpose to update the probability of an event based on the new so new evidence. Find the probability of the one event based upon the occurrence of the another one. Both are some sort of difference. Use the prior knowledge and evidence to compute the revised probability. Here, direct relation between the two events. So now what we have the MLE. MLE is something called that's called maximum likelihood function. So before that, we'll see the PDF that we have seen around like it's the history. So that's the histogram simple sample is there. This is the bell curve. So this can be a mass function, but this line will be the PDF. Like a probability mass function is actually for the for discrete random variable. But when we have the continuous random variable, it will be the PDF, probability distribution functions at all. Okay. So PDF is actually mathematical function that like describes the likelihood of the continuous random variable from a subsample falling within the particular range of the value, not just one value. It's a continuous one. It tells the likelihood of the range of the value in the random variable sample space as the whole sample. It provides the model to visualize how probability is going to vary. It's like a normal scenario. So what is the problem with that? Its estimation relies on the finding of the best PDF, determining its parameter accurately. But random data sample that we consider very small, it will become very difficult to determine what parameter and what probability distribution functions to use. To tackle this one, what we have the it's called MLE, maximum likelihood estimation is going to use it out. Is a method of determining the parameter of normal difference to random sample data or methods of the finding the best fitting. Okay, so for first we'll go into 1, 2, 3, 4, 5. And then we'll go into best five like a fit for that, and then we can get the best result of that. So now we'll come to the like principal component analysis. It's actually a dimensionality. Is to reduce the dimension. So what is the curse of the dimensionality? Like it's going to increase the features should improve the performance, but no, too many features lead to the worse performance. Like a number of the training example, it's going to increase exponentially with the dimensionality and all. So what will happen in that case that the performance will be going to very worst. It's actually dimensionality reduction technique can help us to reduce the number of features into the data sets while keeping the most important information. Like we're not going to lose the information, but the thing is that we are going to reduce the dimensions of that. It changes complex data set by transforming correlated feature into the smaller set of the uncorrelated component. Whenever we have the correlated features, we'll take as a one group, and then we are going to like convert into the with respect to the uncorrelated features and all. So data can be presented into the fewer dimensions. We whenever someone say like I'm going to give too many features and all, it will going to lead to the either underfitting or either overfittings and all. So reduce the dimensionality by the selecting subset. Means either the category cigarette per day, it one subset and then height. Combined with the linear and nonlinear transforms and all. So two feature height and cigarette per day. Both feature increase together, correlated. Can we reduce the number of feature to the one? Yeah, we can do it. So how it will work? It's going to work like a multiple color into the dominant color. Which one is the dominant? Which one is the dominant? Which one is dominant? So it's something. Let's say here we were having some 100 by 100. So now it becomes 3 to 1. So it's a dimensionality reduction and all. It's something PCA uses linear algebra to transform data into the new feature called principal component. It finds this by calculating the eigenvector. It's a SVD actually, and eigenvalue from the covariance matrices. PCS select the two top component with the highest eigenvalue and project the data of onto the simplified data sets in them. So what they will do, we are going to standardize the data using the z is equal to normally the data will be there. Then calculate the covariance matrices. Then calculate the first component. It's something will be the direction of the maximum variance. Then the next best that select direction. Then find out the eigenvalue and eigenvector. Then we'll can get the first PCA, PC1, PC2. How it will look like. Pick the top directions, transform the data. PC1, PC2. Then we can check the variance will be the less. We can go ahead with the. So select the top K component that capture most of the variance like 95%. So variance should means variance should be somewhere 95%. It will go to the second category and all. So, what is the advantage? Multi-correlated handling. Create a new uncorrelated variable to address issue when original features are highly correlated. So, it's going to be, we are going to reduce the uncorrelated features and all. Then eliminate the component with the low variance, enhance the data clarity. Whenever we have the low variance, it's going to club at one place, it will comes under the one category, and then we can separate it. Or we can make the one group. And whenever we have the higher variances, it's called the 95%. So we can cluster into the like two groups in one. Then the data, it's like a data compression. Represent the data with the fewer components, reduce the storage needs, and speeding up the processing. Okay. Then outlier direction. Identify the unusual data points by the showing which one deviates significantly in the reduced spacing out. So, what are the like a disadvantage? It's going to interpretation challenge. Sometimes it will go into like a new component. Sometimes it will not be able to give the clear picture of the original variable. Then one more thing, data scaling sensitivity. Require proper scaling of the data. Otherwise, so what will happen? It's going to result maybe the misleading because we are going to some picture will take into the one pictures. Sometime it can happen, and there is chances of the information loss also. Reducing the dimensions may lose some important information. It too few comments are kept, and it's assume the like linearity works best when the relationship between the like both of them are the it's going to be linear and all. Then what we have the sometime it will be become slow or complex, like complexity will comes into the pictures and all. Risk of the overfitting. User too many components working with a small data set might lead to the model that don't generalize the well. Then what we have the SVM. SVM is actually support vector is a supervised machine learning technique that classifies the data by finding an optimal line or hyperplane that maximize the distance between the each class and in n dimensional space. Let's say I have this one feature, one feature, one feature, one feature. They're going to create a hyperplane so that their distance will be the maximum. So actually, it was developed by the Valmadir and Vapnik, and then it's called the first paper actually support vector method for the functioning approximation, regression estimation, signal processing also. So it's actually used for the classification, but we can use for the regression also. It's called SVR, support vector regression. Okay, so they are going to distinguish between the two classes by finding the optimal hyperplane that maximize the margin between the closed data set point of opposite class, and then they're going to create into the 2D space and all. So that's how they will do it. Maximized margin, class 1, class 2, support vector. It's a hyperplane it's going to create. Okay, so this is called decision plane. Selector version is used for the classification and regression both. It works finding decision planes that separate data into the different class based upon the maximized margins and all. So it actually a linear one, linear SVM. Whenever the data is going to become non-linear, so then there is a terms will call the kernel based the things will come out of the pictures and all. Okay. So support vector machine is going to support vector at the closest data point to the hyperplane that define the class boundary, maximum margin, positive hyperplane, maximum that margin hyperplane, negative hyperplane, and all. Then linear SVM, then the like non-linear SVM will be there. So it's going to create the hyperplane, support vector, margin, then the kernel to enable the non-linear RBF, radius based kernel, then so that the exponential kernels and all will be there. Hard margin, soft margin, then the what we have the regularization C factor will say that the hinge loss, dual problems and all. So again we will have the types of the SPM, linear SPM, then the like non-linear SPM will be there. So now we'll go with the some problems. So according to the central limit theorem, what happened to the distribution of the sum of n independent identically distributed as the n grows? Number of samples will grow. It's going to become the increasingly Gaussian distributions and all. Okay. Second one, what we have the when we have the covariance matrix of the multivariate Gaussian distribution is a proportion to the identity matrices. Shape of the counter is going to constant probability distribution will be going to become circle. Like how it, I'll show you the like explanation also. Using the neo-based classifier for prediction, which rule is going to use to assign the new observation? Which one? We have to use the like a maximum posterior rule. Maximum a posterior. Like it's going to update the probability from the previous one. It's the second one. Given a data set, feature X, class C, naive-Bayes formula is derived by applying which of the following. Like naive-Bayes, how they are going to do? They're going to do based upon the Bayes theorem and then conditional independence of the assumption. What is the probability? In that is the interpretation of the least square cost function. What they will do? Least square cost function is though it's going to maximize the likelihood of the observing the data given to the parameters. What factorization method typically used for the PCA? It's actually singular value decomposition that I told in the starting itself, like PCA and all. For the decision boundary represented by the mathematically in a represent vector machine is going to be a W to the power x plus b, W transpose into x plus b. It's a y mx plus c and all plus b will be there. Which constraint is applied to ensure data are correctly classified by the SVM? It's going to again with the like a W transpose into x plus b greater than 1. How would you the method change if the class maximum likelihood function estimation assume error follow a different distribution so then go like a Gaussian. So in that case, we have to different cost function need to be derived. Okay, so this is the whole about for the today class, and till now what we have discussed as such, we have covered almost all, and now we are ready with now we are. mm Gaussian, that is the model mixture we have to see around. We have seen the Bayesian regression, random forest, KNN, K means, and all. Now we'll go and see how it will look like. Next class. So next class is actually it's going to be MLE. No, illa. It will take about till now what we have seen for the classification. Now we'll see with the regression. Then that we have the advanced machine learning technique like it's a generative model. In that also we'll see self-supervised learning, and the final week will be the again with some examples and all. So any doubt is there till here? So that's all for today from my side. If you have some doubt, so please ask. Shall we wind up for today? Okay. Hopefully there's just there's no doubt. So now we have discussed about supervised. Also we have seen SVM is there, ANN was that all we have seen around. Then unsupervised also we have seen that CNN no, like it's we have seen KNN also we have seen. No, KNN was the supervised one, and then we have seen the unsupervised. We have seen the clustering and all. In the clustering we have seen the two. Like it's agglomerative and then divisive is like that was there. And ensemble learning we have seen the boosting and then bagging we have seen, and now we are left with the regression. We'll see with the Bayesian regression, and we'll go with the self-supervised learning or semi-supervised like a supervised learning. It's called auto encoder or maybe generative adversarial, that the network will see. And with this, I think we'll able to complete. Okay, fine. Okay, then that's all for today. Okay, thank you.